you have the force of friction, you can find it this way. But if you don't have mu, or you don't have the coefficient of friction, you have to find it this way. This. Either way. This or this. In this case, they didn't give the force, the resistive force. They gave the height, but they didn't give the resistive force. Since they didn't give the resistive force, we cannot use this. This will take place of the resistive, of the friction, the resistive force. We cannot use this. We have to go through here. And let's go by inspection. What is delta E? You need to go at the final point, what type of energy? At the initial point, what type of energy? At the final point, what type of energy? There is a resistance. I throw this up. I throw this up. You know that the gravity affects the motion of this. I throw up like this. And I ask, what will be from here to here? What will be the work done by the air resistance, which is the energy released or spent in form of heat by the air resistance. So you can see that if I throw this and this will be two different things with the same speed. You can see if I throw with the same speed, which one is higher? The marker. Why? Why? The mass is not relevant. I mean, if I throw this, what will happen? The same. They have to hit the same at the same time, but not this. Why? A resistance. So I throw with the same speed, the same hand at the same time. Look, it doesn't go the same way because there is a resistance. I am looking for that work missing here, that amount of energy missing here. That's what I am looking for. How can I find it? Second theorem. That energy is somewhere. Where is that energy? Where is this energy spent? That energy released or loose by the cup is somewhere. Where is that energy? In the air. In what form? Heat. Thermal energy. That's the energy spent. But it's somewhere because the energy has to be here. The energy cannot be destroyed, right? Or cannot be created nor destroyed. It's there, but in the air. It's this. That amount of energy released is here, which is equal to delta E. What is E final? Potential or kinetic? This E final, potential or kinetic? Potential. So the only thing to find the work done by the non-conservative force is to find delta E. That's the only thing you need to find. At the end, when this goes to the maximum height, you told me that is potential. What is the formula? mgy. Do you have the mass? Yes. Do you have g? Yes. Do you have the height? Yes. Can you find it? Okay. Minus the initial energy. What is the initial energy? What type of energy from the beginning? What is the type of energy that this have to go up? Kinetic. So you need to subtract the final, which is potential, minus the initial, which is what? Kinetic. And what is the formula for the kinetic energy? mv squared. And it's given the speed, so you have everything to find. This is the way that you approach all these problems. Got it? Okay. And finally, the last problem on this topic is number 10, which I will leave for you to do it. The surface is, the two masses in the figure are released from rest. The question, after the 3 kilogram mass has fallen 1.5 meter, it is moving with a speed of 3.8 meters per second. The question is how much work is done during this time interval by the frictional force on the 2 kilogram mass. The 2 kilogram mass is the one that has frictional force, right? The 3 kilogram mass doesn't have any frictional force. They want the work done by the friction on what mass? On the 2 kilogram mass, right? What of the three theorems we use? second. How many objects you have? You need to go by inspection on the two objects. So, what will be the work done by the friction? We cannot use this. The easier way will be negative mu mg delta x. Do we have delta x? If it's moving 1.5 meters the system, descending 1.5 meters, how much is moving this? The same thing. Do we have delta x?
Yeah, we don't have mu.
But we don't have mu. That's it. We cannot use this. We could use a negative mu mg n of the second mass 2 kilograms mg delta x, but we don't have mu. Stop. We have to go to the other theorem. And we are looking for the work. Very simple. Work done by the friction is equal to delta E. But delta E of everything, if you go by inspection, tell me what is the change. Let's go object by object. Based on the reading, so the 2 kilogram object, the formula will be this, which is delta K for the 2 kilogram object plus delta K for the 3 kilogram object plus delta U for the 2 kilogram object plus delta U for the 3 kilogram object. Is that correct? This is what we call delta E for the whole system. This system start at rest and finish at a velocity. This have delta K. As we can see, the two masses in the figure are released from rest, right?
Yeah.
But finish with 3.8 meters per second. My question is, does this object have kinetic energy at the end? Yes. At the beginning?
No.
No. So we can find the delta K for this guy. This guy, the 3 kilogram object, which is descending, at the end has kinetic energy.
Yes.
At the beginning? No. And what will be the formula? 1/2. What mass? 3 b squared. And we have. So let's go by inspection to this guy. Delta U for 2 kilogram object. Is there any change in potential energy for the 2 kilogram object? Change with respect to itself, not with respect. This is moving from here to here. What is the change in potential energy?
0.
Why?
No change in height.
No change in height. No change in height. Does this object have change in potential energy? If I do mg with respect to the ground, mg3, and mg3, let's say that this is 1 meter to the ground, mg times 1 meter, and mg times 1 meter, subtract, will be 0. There is no change in potential energy. Good. Does this guy has a change in potential energy? Is increase or decrease? When it's descending, increase or decrease? Will be positive or negative? Negative. Mg what? Mg y. And how much is y? Whatever they give. So, but it's positive or negative? Negative. So here we are working instead of with EI or E final, we are using delta because what we know is the changes. It's easier to work with changes than with EI minus E final or E final minus E initial. It's better to use changes rather than E final and E initial. You can work either way, but it's easier to work. This is E final minus E initial. So this will be the same. E final minus E initial, right? E final for what? For the second object. So it will be like this. K of the second plus potential of the second plus final plus kinetic of the third plus potential of the third. All this is this. All this is E final. Equal to kinetic of the second initial plus kinetic or plus potential of the second initial plus kinetic of the third final, initial, sorry, plus U of the third initial. These and these are equivalent. These and these are equivalent. But what will be easier to work with? This or this? Will be easier to work with this. But they are equivalent.